Before we implement multivariate linear regression model in Python from scratch, let's discuss its algorithm and pseudocode. So here we are given the design matrix X and the dimension of X is n number of features times number of training examples m, and also we are given the ground truth label y vector and its dimension is 1 times m. So we are given this. Now, first of all, step 1. Here in step 1, we are going to initialize weights and bias. So n features are there, so we'll have n number of weights, w1, w2, wn, and this is a row vector and this is our weight vector, w vector, and also we have bias b. So we have to initialize them. Why we need to initialize them? Because when I was describing the gradient descent, and in gradient descent I said, okay, if this is a convex function and if this is the point P in the input plane, then we need to iterate through in order to reach to the global minimum. That's why we need to initialize. So this point is the point of initialization. And if this is a convex function, so initialization of weights and bias can be zero also. So we can initialize from the origin itself. So we are left with two choices. Choice one, we can initialize all of them to be zero. This is also zero. So this is choice one. Or we can initialize this randomly, w1, w2, wn randomly, but we need to make sure that the variation of this random initialization should not be too high. Like w1 should not be of the order of 1000, 10,000, and w2 should be 10 or so, something like that. So we need to avoid it. So we are left with these two choices. And in NumPy, we can easily initialize using NP. NP stands for NumPy, NP dot zeros vector, and the dimension of this will be length of this w vector. Here n is here, so we'll have 1 n. 1 stands for number of rows, which is 1, and n for number of columns. This is for the w vector, right? So w vector is this one, or w vector may be np dot random dot rand n. N stands for standard normal distribution, that is bell-shaped curve. So rand n, and here we can put 1n. So this way we can initialize it. And for bias, b can be safely initialized to be 0. So this is how we can initialize weights and bias. This is step 1. Let's discuss step 2. Step 2 is, once we have initialized w vector and b, then we are going to find z vector, which we have already found. We have derived z vector as w vector matrix multiplication of the weight vector with the matrix x, that is the design matrix, plus b, that is the bias vector, right? So this is step 2, and all these steps can be implemented using function. So here we can define this function, and that is forward propagation. Forward propagation because we are moving forward. X design matrix is there, and also we are having w vector, then b vector is also there. So we are going to implement it using the function define forward propagation. For prop I'm writing, and here I'm passing the parameters w vector, then we have x vector, sorry, x matrix, and also the b bias here. So then we can z vector is equal to write down this. So now in numpy, whenever we need to multiply vectors with this matrix, we can put np dot for matrix multiplication, and here we have w and x, w vector x, and then we need to add this b by us. So in numpy actually we can just use addition with this scalar addition, because broadcasting can be there in numpy. So b will be broadcasted to the vector b vector. So this is how we can implement. This is step 2. We have found z vector. Now in step 3, so in step 3 we will find the cost function z. So define our cost and cost function. In order to find cost function, we need to find y vector and also z vector, which we have already calculated. So z vector will be, and also 1 by basically cost is 1 by 2m summation yi zi minus yi whole squared. So we can have this. So here z is equal to 1 over 2m. M is, by the way, m can be found using np or y dot shape, and its shape is, 1 stands for the column. So the number of columns here will be m here. So m is, we are getting m now. So in numpy we can have this syntax to find the shape of y vector. So j is equal to, here we can say, okay, this j is equal to 1 by 2m and summation of zi minus yi whole squared. So this multiplied by uh, whole squared. So we have np dot sum. We are going to sum of what? Sum of the square of this. So np dot sum z vector minus y vector, and basically when we will square it, so z vector z minus y, and then when we square it all the elements will be squared, and then np dot sum will take the sum of all the squared of the difference of z vector and y vector. So basically this square here, we can say np dot sum, or maybe we can say np dot square. Here also we can put like this np dot square of this vector. So we'll be getting j, and then we can return our cost function z. This is step 3. And now let's move on to step 4. Step 4 will be back propagation. Once we have calculated z vector and z, then we will be needing z vector in back propagation. Step 4 will be our define backprop, and in back propagation what we are going to need is z vector, right? And then also y vector will be needing it. So then here we can say that we need to find del z over del z vector, and this is nothing but we know 1 by m zi minus yi is, we have already deduced it. So this ith term is nothing but 1 by m times zi minus yi. So how we can implement it? So I'm using the symbol dz. In programming we'll be using dz to represent the vector del j over del z vector, and this dz is equal to 1 by m, and all the elements are like this. So 1 by m times z vector, we have this g vector minus y vector. So when we subtract z and minus y from z, then and multiplied with 1 by m, then we will be getting this dz vector. This dz vector we will be getting. This is step number 4. And here we once we have this dz, we remember two equations for the back propagation: del z over del w vector. And for this I am using the symbol dw vector, and this dw vector is nothing but del z by del z. This del z by del z times this is the matrix multiplication with the transpose of x transpose. So how will we implement it? This is our dz times dz dot x transpose, right? So in numpy we can say this is np dot, so I'm taking the dot, basically the matrix multiplication of dz and transpose of x. So x dot t, in numpy we use this one, x dot t. So we have this dw now, and db as a sum of all the elements of dz vector. So db is np dot sum, np dot sum of what? Sum of dz. So this will basically add up all the elements of dz vector. So we have dw and dv. Now this is our back propagation step. So let's return dw and return dw db. So then we are return dw, which is the gradient, del j over del w1, del j over del w2, so on, del j over del w, and this is a vector, and also db. Now in step 5 is the gradient descent update, ZD update, and this is basically very simple one. So here in this function, basically all of the steps will be implemented using function. So ZD update, maybe I'm saying definition ZD update, and here we'll be passing dw, db, wb. So we'll be passing w vector, b, and then dw, db, and also one of the hyperparameter alpha. Hyperparameter means we have to set it up manually. We tune it manually. So alpha may be 0.0001, 0.002, something like that. So here our famous gradient descent update equation is W is updated as W minus learning rate alpha times dw, and we have this w vector also, this vector we have, and dw is basically the vector, row vector, and this row vector is multiplied with alpha. So basically all the elements of this row vector will be multiplied. So using this equation we are sure that w1 is updated as w1 minus alpha times del z over del w1, w2 as w2 minus alpha del z over del w2, and so on. And similarly, for the update of b, we have b is equal to b minus learning rate alpha times del z over del b, which is represented by db. So this is how the update gradient descent update follows, the step 5. Now let's move on to the final step, that is our model step, step 6. And in step 6 we will use all those steps 1 through 5, and all those functions will be using. So in step 6, so let's define our linear regression model, LRM. multilinear regression model. Generally I'm using this LR definition, def linear regression model. So what parameters will be passing here? Let's see. Here we are going to pass the training set, and training set is represented as xtrain, and its corresponding y label, that is y train, x validation, y validation. So how we are going to calculate this train and validation? What do you mean by validation also? Let's see. See, we are given the data set x and y. So what we'll do, we will split the data set x and y into two segments, training set and validation set. So here x train will be of the same, number of features will be same, but here the training examples which we have used m, so that training example will be split here, so n times m1, and similarly y train will have say 1 times m1. Similarly x validation will have say n times m2, y val will have say 1 times m2. By the way, this x val and y val is used to see how well our model is performing on unseen data. So train x train, y train will be used for training purposes, and this will be used for the calculation, for the to check how well it is performing on unseen data. So basically x and y, which is split into these two sets, so we are passing this 2, and then we will also pass the learning rate alpha, and this alpha is again tuned manually. We will say alpha is 0.00 something 1, so alpha and whatever this value will be alpha, and then also one another hyperparameter is there, that is that is epochs. What is epochs here? Epochs is the number of iterations through all the training examples. So number of iterations, look here. So basically what exactly means non number of iterations here? So for this two-dimensional case here, we see first iteration, second iteration, third iteration, and uh, so all through the iterations it is going to reach to the global minimum. So this number of iteration is known as epochs. So basically it is using all the x train and y train, right? So that's why it is epochs. So epochs may be set like 10,000, 1,000, 2,000. We need to set it manually and check how well it is performing on validation and the validation set, in fact. So that's why validation set is there to check how well it is performing using alpha and epochs. So we can every time change alpha and epochs to find the accuracy over the validation set. So these are the parameters we'll be passing in our LR model. Then what other steps we will be using? So here we will carry out step 1, that is the either this or this. So here we'll basically initialize the weights and bias. Once weights and bias is initialized, we'll use the iterations for I is equal to 1 to the number of epochs here. When it is, let's say, 10,000, so I is equal to 1 to 10,000, so I is equal to 1 to epochs. So here we'll be carrying out some steps here. So again, once we have initialized w vector, so we'll use step 2. So here use step 2 to find z vector. And then again we will use step 3 to find our cost z, and then what we can do, we can store all the cost, or maybe like cost for every 10 iterations, we can store all those in a list for the plotting purpose, so how well the cost is increasing or decreasing, something like that. So cost, we have this cost, once it is calculated we can store it, okay, to check how well this cost is there, right? So this is basically the training cost, because here we will be using x train and y train here for step 2, step 3. For step 2 also we are using x train here, right? Step, when we pass step 2 we'll be basically passing, x train here. So use x train to carry out step 2, then step 3, then we have step 4, then finally we have step 4. Once we have step 4, all these steps are for x train, y train. So step 4, here we'll be passing z, y train, here we'll be passing y train, z, which has been returned from step 3, likewise. And then we have the next step as step 5. Step 5, which is gradient descent, update, then W and B will be returned here, return W and B. So, uh, so basically, this is how the steps for the training are going on. Also, we need to check how well our model is performing on validation set. So what we'll do is to find some accuracy indicator like mean absolute error, right? So what we'll do, mean absolute error is nothing but, is defined as 1 by m summation of you know this thing, zi minus yi. Absolute is there, so I'm putting mod here. So this is mean absolute error, and we can implement it using Python. In Python, that is 1 by m, and this is sum, np.sum, and np.abs will be, np.abs will be for finding out absolute value. So np.abs z minus y, right? And then 1 by m times here. So then what we'll do is we'll find 1 by m np.abs z for the training and the validation set. So y train will find MAE, mean absolute error, for both, for the training and the validation set. So for the training set it will be y train, and here z will be found for the z train, and this is nothing but MAE train here. And similarly for MAE validation will also be there, 1 by m np dot abs z. Similarly we will be calculating all those steps for step 2 for the validation set, w vector times x val plus b vector, and then we'll be finding MAE validation. So basically MAE val will tell us how well our model is performing on unseen data. Actually, the same W vector which has been updated is used to find MAE val. So these are the steps we need to carry out. And also later on we can use this stored value of the cost to plot the cost as a function of iteration to check how the graph of the cost is looking like. Generally, it should decrease, the cost should decrease with number of iterations. That's it. And in the next video, we will implement all those steps in Python from scratch. Thank you.